Now we will see one theorem, that is internal bisector of a theorem, internal bisector of a triangle. The theorem states that the internal bisector of an angle of a triangle divides the opposite sides, divide the opposite side internally in the ratio of the side containing the angle, the sides containing the angle. Meaning of this statement is that here triangle ABC is drawn and AD is the bisector of the angle. AD is the bisector of the angle A. Means due to AD, the angle A or BAC, angle BAC divided into two equal angles, that is angle 1 and angle 2. So these are the two equal angles. Here means angle 1 equal to angle 2. So this is the bisector of the angle. And this bisector of the angle intersects the opposite side of A, that is BC, in a point D, and this D divides the side BC, that is BD and DC, in such a way that the ratio of, that is AD upon AC, means BD upon DC equal to AD upon AC. Again, listen that the internal bisector of an angle of a triangle, AD is the internal bisector of an angle A, divides the opposite side, BC internally in the ratio of the sides containing the angle. Now the opposite side BC gets divided, means BD upon DC is equal to the sides containing the angle, means angle A is formed due to the side AB and AC. So BD upon DC equal to AB upon AC. So this is the statement of our theorem. And now here in the figure there is construction, that is we have to produce BA to E and then join EC. Here we have to draw EC which is parallel to AD. Means we have to draw the CE which is parallel to DA here. And now we will see the theorem. First of all, given means information of the figure. Here in a triangle A B C, AD is the bisector of angle A. So in a triangle ABC, AD is the internal bisector of angle A and meets BC, means this bisector meets BC in a point D. Now to prove, we have to prove that BD upon DC is equal to AB upon AC. So BD upon DC is equal to AB upon AC, we have to prove. And now construction, draw CE parallel DA. So we have to draw CE which is parallel to DA. To meet BA produced in E, means we have to produce BA to E, and in a point E, CE intersect, which is CE is parallel to DA. And now proof. CE parallel to DA and AC is a transversal. Here CE and DA. I have drawn here separate figure, that is CE and DA both are parallel, and here AC means AC is the transversal, and due to this transversal we get alternate angle, means pair of alternate angle. Here 2 and 3 are the alternate angle, and we know that if a transversal drawn or transversal of the parallel lines divides, or the alternate angles formed due to the transversal of parallel lines are equal, means transversal alternate angles are always equal. So here angle 2 equal to angle 3, equation number 1. Now CE parallel DA, again we know that CE is parallel to DA, but here I have drawn here CE and DA, these are the two parallel lines, and now EB is a transversal, and due to this transversal angle 1 and angle 4, two angles are formed which are corresponding angles, and corresponding angles formed due to the transversal of a parallel line are always equal, and therefore angle 1 equal to angle 4, angle 1 equal to angle 4. So these are the corresponding angles. Now we know that AD is the bisector of angle A, and therefore angle 1 equal to angle 2. We have mentioned here angle 1 equal to angle 2. So angle 1 equal to angle 2. This is the equation number 3. Here equation 1, angle 2 equal to angle 3. Angle 1 equal to angle 4 is equation 2, and angle 1 equal to angle 2. From equation 3, it is being seen that angle 1 and angle 2, both the LHS of equation 1 and 2 are equal, and therefore RHS must be equal. So angle 3 equal to angle 4. From equation 1, 2 and 3 we get angle 3 equal to angle 4. Here it is seen that angle 3 and angle 4 both are equal angles, and if we consider the triangle ACE, then the two angles of triangle ACE are equal, means if the two angles are equal, then we know that is the isosceles triangle, and side opposite to equal angles are also equals, means opposite side of 3 is AE and opposite side of 4 is AC, and therefore we can say that AE equal to AC. Means if the two angles are equal, then the side opposite to equal angles are equal, and therefore AE equal to AC. Means triangle ACE is an isosceles triangle. Here AE equal to AC, and that is equal to equation number 4. And now we will consider here the triangle. Here if we consider the triangle, then it is seen that in a triangle EBC or BCE, AD is parallel to the side CE, and in this way we can apply the basic proportionality theorem, because if a line is drawn parallel to one side of a triangle intersecting the two sides, then it divides the two sides in the same ratio, means AD is parallel to the one side of the triangle BCE, and therefore we can apply here the BPT, and therefore according to BPT we can write that BD upon DC, BD upon DC. BD upon DC is equal to BA upon AE, means BA upon AE, or we can write here BD upon DC is equal to AB upon AE. In this way we have proved this theorem, that is internal bisector of an angle of a triangle. Now we will see one example, that is if the bisector of an angle of a triangle bisects the opposite side, prove that the triangle is an isosceles. Means here the bisector of an angle AD is the bisector of angle A, and this bisector also bisects the opposite side of the angle, means it bisects BC, means BD equal to DC. Here since AD is the bisector, B is the midpoint of BC, and if B is midpoint, then BD equal to DC. And then we have to prove that the given triangle ABC is an isosceles triangle. If it is an isosceles, then we have to prove that AB equal to AC. Our proof is AB equal to AC. Here it is given, means the information of the figure. So in a triangle ABC, the bisector AD of angle A, means AD is the bisector of angle A, so these two angles are equal. The side also it bisects the side BC. Just now I have told you that AD is the bisector of side BC, means B is the midpoint of BC, and therefore it will be BD equal to BC. And now we have to prove that AB equal to BC. If such a condition is there, then the given triangle is an isosceles triangle, means we have to prove that AB equal to AC. And now proof. In a triangle ABC, AD is the bisector of angle A. Here again I will tell you that AD is the bisector of angle A, so these two angles are equal. By angle bisector theorem, we can write that BD upon DC is equal to AB upon AC. So AB upon AC is equal to BD upon DC. But AD bisects side BC. We know that AD bisects side BC means B is the midpoint of BC, and therefore BD equal to DC, and therefore BD equal to DC. And now if we write the value of BD, means here BD, if we remove BD and instead of BD we will write here DC. So DC upon DC we will get AB upon AC as it is equal to DC upon DC, and DC upon DC means 1. So AB upon AC is equal to 1. Here AC is multiplied. If we transform it to the another side, then it will multiply to 1. So AB equal to AC. So we will get here AB equal to AC. And the triangle having two sides equal is an always isosceles triangle, and therefore triangle ABC is an isosceles triangle. Now we have more properties on basic proportionality theorem. We have to see now. So we will see now the first theorem, which is dependent on basic proportionality theorem. So the theorem states that the line drawn from the midpoint of one side of a triangle parallel to another side, then it bisects the third side. Here it is given that if you draw a triangle, let it be ABC, and take a midpoint of one side, that is it is D. So D is the midpoint of side AB. If D is midpoint, then we will get here AD equal to BD or DB, whatever it means. So AD equal to DB. And now through the midpoint D, we have to draw a line which is parallel to the another side. Means DE is the side line which is parallel to the side BC. So it is given that DE parallel BC. Means two conditions are given here. First condition is that the line DE is passing to the midpoint of AB. So D is the midpoint, means AD equal to BD. And the another condition is that this line DD is parallel to the second side BC. And if such a condition is there, then we have to prove that the DE also bisects the third side. Means we have to prove that E is the midpoint of AC or AE equal to EC. AE equal to EC. Means we have to prove that E is the midpoint of EC, and therefore DE passes or bisects the third side. So this will be our proof, and now we will see step by step that first of all here ABC is drawn, D is the midpoint, so D is the midpoint of AB, so AD equal to DB we have, and we have shown the same marks so that we will get AD and BD equal. Now, given in a triangle ABC, D is the midpoint of AB, D is the midpoint of AB, and the line DE is parallel to BC. This line DE is parallel to BC. DE meeting AC in E. DE meeting AC in E. So DE is intersecting the side in a point E. Now to prove that E is midpoint of AC. So we have to prove that E is midpoint of AC or AE equal to EC. That is AE equal to EC. And now we will see proof. In a triangle ABC, DE parallel BC. We can consider both the figures are same. Here it is given that DE is parallel to BC. Then and then we can apply the basic proportionality theorem, that is BPT, and then we will get AD upon DB is equal to AE upon EC. So in a triangle ABC, DE parallel BC, and therefore by DPT AD upon DB equal to AE upon EC, and this is equation number 1. But we know that DD is a midpoint, so AD equal to DB, and therefore AD equal to DB. So from equation 1 we can remove AD because value of AD is DB. So instead of AD we will write there DB. So DB upon DB means the equation 1 will become DB upon DB equal to AE upon EC. Here DB will get cancelled and we will get here 1. So AE upon EC is equal to 1, and now this EC is divided, it will multiply to 1. So EC is equal to AE or AE equal to EC. Here AE equal to EC means E is the midpoint of AC, and in this way the line DE bisects the third side AC. Bisect the third side AC. In this way, we have proved the theorem. Our next theorem is that the line joining the midpoints of a triangle is parallel to the third side. The line joining the midpoints of two sides of a triangle is parallel to the third side. Here, in a triangle ABC, D and E are the midpoints of AB and AC respectively. Means D is midpoint of AB and E is midpoint of AC, and D is the line joining these two midpoints. And if such a condition is there, then the line joining the midpoints of the two sides is parallel to the third side, or D is parallel to BC. We have to prove that D is parallel to BC. And now we will see the theorem. First of all, write given. Means we have to write the information of the figure. In a triangle ABC, D and E are the midpoints of the sides AB and AC respectively. Then we have to prove that D parallel BC. D is parallel to BC. And proof is, since D and E are the midpoints of AB and AC respectively, means if D is the midpoint of AB, then AD equal to DB and AE equal to EC. Means since D and E are the midpoints of AB and AC respectively, then we get AD equal to DB and AE equal to EC. And now, if we take the ratio, means AD upon DB, then we know that length of AD and length of DB is equal, and therefore the ratio will be 1, or division will be 1. So AD upon DB is equal to 1. Similarly, AE upon EC it will be 1. And now here RHS of both the ratios, RHS of both the ratios is same, and therefore LHS must be same. So AD upon DB equal to AE upon EC. From this equation, it is seen that AD and DB, AD upon DB equal to AE upon EC. And the converse of basic proportionality theorem states that the line which divides the two sides in same ratio is a parallel to the third side. We know that AD upon DB equal to AE upon EC, means side AB and AC are divided in the same ratio, and therefore the line which divides the two sides in the same ratio is a parallel to the third side, is DE parallel BC. Therefore the line divides the sides AB and AC of triangle ABC in the same ratio. Hence, by the converse of basic proportionality theorem, DE parallel BC. In this way, we have proved the theorem, and now we will see the next theorem, that is the diagonals of a trapezium divide each other proportionally. Proportionally means in the same ratio. Proportionally means in the same ratio, means both the diagonals divides in the same ratio. Here A, B, C, D is a trapezium. AC and DD are the two diagonals which intersect each other in a point E. So the diagonals of trapezium divides each other proportionally. To prove this theorem, we have to write first given, means write the information about our figure. So in a trapezium ABCD, diagonals AC and BD intersect each other in a point E. So AC and BD are the diagonals, they intersect each other in a point E. Then to prove that both the diagonals divides each other in the same ratio, means here DE upon EB equal to CE upon EA. So both the ratios are equal. We have to prove that both the ratios are equal. To prove DE upon EB, DE upon EB equal to CE upon EA, CE upon EA. Here construction is done. And that construction is draw EF parallel BA parallel CD. Means to the point E, we have drawn segment EF which is parallel to AB as well as EF is parallel to BC. EF is parallel to BC because we know that a trapezium is a quadrilateral in which the pair of opposite sides, only one pair of opposite sides is parallel to each other. Means AB and BC, they must be parallel. The another pair is not parallel. Only AB and BC are parallel, and we have to draw EF parallel to AB as well as BC. And now the EF meets side DA in a point F. In this way we have done our construction. And now proof. In a triangle ADB, in a triangle ADB, this is the triangle we have to consider. Here I have drawn the figure ADB, and in this EF is parallel to AB. Here EF is parallel to AB, means some part of the diagram I have drawn here, and in this triangle DAB, EF is parallel to the one side of the triangle. If the line is parallel to the one side of a triangle, then it divides the two sides in the same ratio, and therefore DF upon FA is equal to DE upon EB. Is DE upon EB is equal to DF upon FA, and this is equation number 1, and the reason is basic proportionality theorem or BPD. Similarly, we have to consider another triangle, that is DAC. Here DAC, that is the triangle, and in this triangle here I have drawn same figure, that is DAC, and in that figure EF is parallel to DC or CD. EF is parallel to CD. Here in a triangle CDA, EF parallel CD. Then we can apply here basic proportionality theorem, because one line of a line is parallel to the one side of the triangle, and therefore we can get C upon EA is equal to DF upon FA according to basic proportionality theorem. Here C upon EA is equal to DF upon FA. This is equation number 2. From equation 1 and 2 we get that DF upon FA, and here also DF upon FA, means RHS of both the equations are same, so LHS must be same. That is DE upon EB equal to CE upon EA. Therefore from 1 and 2 we have written DF upon EB equal to CE upon EA, and in this way we have proved that the diagonals of the trapezium, they both divide each other proportionally. Here we have to see a theorem, that is, if the diagonals of a quadrilateral divide each other proportionally, then it is a trapezium. In the previous theorem we have seen that in a trapezium the diagonals of the trapezium divides each other proportionally, and the converse of the theorem is that if the diagonals of a quadrilateral divide each other proportionally, then it is a trapezium. So here A, B, C, D is a trapezium, and DB and CA are the two diagonals which intersect each other in a point E. So here we have to write given means the information about the figure, means a quadrilateral, because we are not going to say it is a trapezium, we have to prove that it is a trapezium. So ABCD is a simple quadrilateral. So in a quadrilateral ABCD, diagonals AC and BD, diagonal AC and BD intersect at E such that proportionally, means here DE upon EB is equal to CE upon EA, means both the ratio must be equal, and if they are equal then we say that they divide each other proportionally. Now to prove that a quadrilateral ABCD is a trapezium, now for this proof, it is sufficient to prove that AB parallel BC, means if the pair of opposite side, only one pair of opposite side is parallel, then the quadrilateral is a trapezium. So it is sufficient to prove that AB parallel DC. Here we have made some construction, that is draw EF parallel BA. Draw EF parallel BA, meeting AD in F. Meeting AD in F. Now, proof of this theorem is that in a triangle ABD, we have to consider only ABD. In a triangle ABD, in a triangle ABD, if we remove this part, then we will get the same figure here. So EF or FE is parallel to AB, and here we can apply the basic proportionality theorem, that is DPT, and then we get DF upon FA is equal to DE upon EB. So in a triangle ABD, EF is parallel to BA, EF is parallel to BA, and therefore DE upon EB or DF upon FA is equal to DE upon AB, and this is equation number 1. But it is given that the diagonals AC and BD intersect at E such that DE upon AB equal to CE upon EA, means we have given the information, that is DE upon AB is equal to CE upon EA, and that is equation number 2. The reason is given, and now here it is seen that DE upon EB, DE upon EB, so value are same, so DF upon FA is equal to CE upon EA, means from equation 1 and 2 we get DF upon FA is equal to CE upon EA, and therefore if we observe the figure, it is seen that in a triangle DCA, in a triangle DCA, we get here DF upon FA is equal to CE upon EA. CE upon EA means the inner triangle DCA, the two sides are divided. Two sides are divided proportionally, and therefore the line EF, that is EF is parallel to DC. EF is parallel to DC, and therefore EF is parallel to BA. EF is parallel to BA. We know that EF is parallel to BA and AB is parallel to DC. We get here EF parallel to BA, DC parallel to BA, and therefore AB parallel to DC. Means we have proved that AB is parallel to DC. Means one pair of the opposite sides of the quadrilateral is parallel, and therefore ABCD is a trapezium. In this way, we have proved the theorem. Now there is one more important theorem, and we are going to see that here L, M, N, these are the three parallel lines. AB and CD, these are the two transversal of the three lines. Here line AB intersects L in a point P. AB intersects line M in a Q, while AB intersects line N in a R. Similarly, CD, line CD or transversal CD intersects L, M, N lines in a point E, F and G respectively. So here PQ. So PQ is a intersect. So this segment formed due to the transversal is called as intersect. Similarly, QR is also a intersect. Here EF is also intersect. FG intersect. So the theorem states that if three or more parallel lines are intersected by two transversals, means these two transversals, then prove that the intersect means the segment PQ, QR, EF and FG. The intersects made by them on the transversals are proportional. Means we have to, if we consider the intercept on AB is PQ and QR. So PQ upon QR, and the intercept on the transversal are EF and FG. So we have to see that EF upon FG, and we have to prove that PQ upon QR is equal to EF upon FG. So we have to prove here. Now it is given that three parallel lines here LMN are cut by the transversals AB and CD. Here AB and CD, these are the transversal, and due to the cut means AB cut the line LMN in a point PQR, and CD transversal cuts these three lines in a point EFG respectively. Then we have to prove that the ratio of the intersects, that is PQ upon QR, equal to EF upon FG. And now construction is done here. So draw PL parallel CD. From the point P, we have to draw a line PL which is parallel to CD, and it intersects M and L respectively. Then proof, since PM parallel EM, it is PM is parallel to EM. Similarly, P and MF they are also parallel. Means opposite sides of this quadrilateral are parallel, and therefore PMFE is a parallelogram. PMFE is a parallelogram. PMFE is a parallelogram. And if the parallelograms, they are parallelogram, then we have PM equal to EF. Is PM equal to EF. Means opposite sides are equal. We know the property of parallelogram that the opposite sides of the parallelogram, they are parallel, but they are equal also, and therefore PM equal to EF. So this is equation number 1, reason opposite sides of a parallelogram. Now we will consider another, that is ML is parallel to FG. Similarly, MF is parallel to LG, and therefore quadrilateral MLGF is also a parallelogram, and therefore again we have to apply the same property that opposite sides of the parallelogram are equal, therefore ML is equal to FG. So we will get that ML is equal to FG, that is the second equation, and reason is opposite sides of a parallelogram. Now we have to consider triangle PRL. Here triangle PRL is there, and in that triangle QN is parallel to RL. QN is parallel to RL, and then we can apply the basic proportionality theorem or Thales theorem in this triangle, so that we will get PQ upon QR is equal to PM upon ML. So we will get here PQ upon QR is equal to PM upon ML by BPD or basic proportionality theorem. And now PQ upon QR, right, as it is equal to PM. What is the value of PM? PM is EM. So right here EM. Then EML, what is the value of ML? ML is equal to FG. So we here write EF upon FG. From equation 1 and 2 we can write, and in this way we have proved that PQ upon QR is equal to EF upon FG. EF upon FG. So this was our fifth theorem, and it is very important theorem.